Hello there you guys, it's Anand from Ace, and today we're solving the mechanics paper from February-March 2023, variant 4.2. So let's get started. A crate of mass 200 kilograms is being pulled at a constant speed along a horizontal ground by a horizontal rope attached to a winch. The winch is working at a constant rate of 4.5 kilowatts, and there is a constant resistance to motion of the crate of magnitude 600 newtons. Find the time that it takes for the crate to move a distance of 15 meters. Okay, let's draw a simple diagram of the situation. A resistance to motion is acting on the crate that is of magnitude 600 newtons. A forward force should also act in the forward direction. Let's call that F sub F, okay? This is there to balance out the constant resistance to motion because the entire crate is moving at constant speed. And in order to balance out the backward force, the forward force must also be equal to 600 newtons. So we know the value of the forward force. We also know the value of the power of the crate. We can simply put this in our formula. P equals forward force times the velocity. We can subject V to find the value of the velocity at which the crate is traveling at. And that is found to be 7.5 meters per second. Okay, we know the value of velocity. We know the value of the distance. We can input all of that in our kinematics equation that involves zero acceleration. The value of S is 15, and the value of V is 7.5, and the value of T is found to be 2 seconds. Part B. The rope breaks after the crate has moved 15 meters. Find the time taken after the rope breaks for the crate to come to rest. So after the crate has moved 15 meters, the forward force is gone. So there is no force exerted by the rope. Thus, the only force that's acting on the crate is 600 newtons. Thus, there is a resultant force acting in the backward direction. So there must also be a negative acceleration that's slowing this crate down. Alright, we can find that value of negative acceleration by simply inputting our values in the Newton's second law of motion. We have the resultant force, that is 0 minus 600. Forward force is of magnitude 0, and the backward force is of magnitude 600. We know the mass of the crate, that's 200 kilograms, and we can simply subject A to find the value of the negative acceleration. So when the crate comes to rest, we know the value of the final velocity, that's 0. The value of V when the crate has traveled 15 meters is 7.5 because it's traveling at constant velocity. So we can input that in U. We know the value of the negative acceleration, and that is negative 3 meters per second squared. We can simply subject T to find the value of the time taken for which the crate comes to rest. Problem number 2. Particle P is projected vertically upwards from the horizontal ground with speed 15 meters per second. Find the speed of P when it is 10 meters above the ground. So when the particle is projected vertically upwards, we know that the value of G is 10 meters per second squared, and this G is acting in the opposite direction of the motion of the particle. So this would be negative 10 meters per second squared. So now we have a collection of values. That's the acceleration, the speed, and the initial speed specifically, and the distance. So we can use our kinematics formula, v squared equals u squared plus 2as, and input all of our values, and then subject v to find the final velocity of particle P at 10 meters above the ground. So yeah, part B. At the same instant that P is projected, a second particle, Q, is dropped from a height of 18 meters above the ground in the same vertical line as P. Find the height above the ground at which the two particles collide. Whenever we are dealing with two particles and they want us to find something that's relating those two particles, we'll have to find two equations that models a property of these particles. In this case, it would be the height above which the particles are at from the ground at time t. So let's consider q. When time equals 0, the height of q above the ground is 18. Okay, and as time increases, the height of q decreases. At what rate? That rate is given by s equals ut plus half at squared. When time equals, well, q is dropped from rest, so u would be 0, and a would be positive 10. Why positive 10? Because the motion of q is in the same direction as g. So that is the rate at which the height decreases. So if that's the decrement factor or decrement term, we will find the height of q above the ground using this equation. We'll just have to decrement this term from 18. So the height of q would be given by 18 minus exactly that term. So h would, once we simplify this, hq would be equal to 18 minus 5t squared. For p, we just simply use the same formula, s equals ut plus half at squared. Our initial value of u is 15. G is negative 10 because the motion of p is in the opposite direction of the g of g. So our value of g is negative 10 in that case. Once we simplify that, it would be 15t minus 5t squared. Now, at the point when the particles collide, the height above which both these particles are above the ground is the same. So HQ is equal to HP. Therefore, once we equate these two equations, luckily the quadratic terms get cancelled out and we get 18 is equal to 15t. And we find the t to be 1.2 seconds. After that, we can input this value in any one of those two equations that we found earlier, and then we can find the height at which the two particles collide. Problem number 3. A particle moves in a straight line from rest from point O. The acceleration of the particle at time t seconds after leaving O is a meter per second, where a is equal to 4 times t to the half. Find the speed of the particle when t equals 9. Okay, so we have an expression of a in terms of t. We can simply find the expression for v by integrating a with respect to t. Once we integrate it, we get a constant term plus c. In the prompt above, it's given that the particle starts from rest. So at point O, time equals 0. So when t equals 0, v would be equal to 0, and the constant term is found to be 0. Thus, our expression for v is simply 8 over 3, t to the 3 by 2. We simply input our value of t inside of our expression to find the value of v at t equals 9. Part B, find the time after leaving O at which the speed in meter per second and the distance traveled in meters are numerically equal. So they want us to deal with speed and distance, okay? So we have an expression for v. If we ignore the direction, we can just consider this to be the expression for speed. We just need to find the distance expression. We can simply do that by integrating v again. Once we integrate v, we get another constant term. We know that the displacement of displacement of the particle is 0 at time equals 0 because it is at O. The displacement of the particle from O would be just 0. So at time equals 0, which means it's at O, the displacement would be equal to 0. Thus, the constant term would be equal to 0. So once we simplify our expression, we get the displacement to be 16 over 15 t to the 5 over 2. We want the distance to be equal to the speed or in other words, once we take into account the direction, the displacement to be equal to the velocity. So we know our displacement expression. We also know our velocity expression. Once we equate those two together, we have this following relation. We can take t to the 3 by 2 common, and we'll find these two terms. For this entire expression to be equal to 0, either this term, t to the 3 by 2, has to be equal to 0. But since we want to find the time after leaving O, of the particle after leaving O, we cannot take t to be equal to 0, because at t equals 0, the particle is at O. So the other term will give us the correct answer. So once we equate t, we find t to be equal to 2.5 seconds. Problem number 4. A toy railway locomotive of mass 0.8 kilograms is towing a truck of mass 0.4 kilograms on a straight horizontal track at a constant speed of 2 meters per second. There is a constant resistance of force of magnitude 0.2 newtons on the locomotive, but no resistance force on the truck. There's a light, rigid horizontal coupling connecting the locomotive and the truck. So let's draw a simple diagram of our system. Locomotive, that's the truck. This is the coupling. This is the tension in the coupling. And we know that a force of 0.2 newtons is acting on the locomotive. So let's consider the entire system. So when we consider the entire system, the tensions get cancelled out because they're acting in opposite directions. And the system is moving at a constant speed. So there must be something that balances out the resistance to motion. And that should be the forward force that's exerted by the locomotive. Now, if we consider, let's say, the truck, for the truck to move in with constant velocity, the forward force of the truck has to be equal to the backward force. Now, no backward forces act on the truck. It's 0. And for the truck to move at constant speed, the forward force must be equal to the backward force. Since backward force is equal to 0, the forward force, which is T, should also be equal to 0. Thus, the tension in the coupling is 0 newtons. Part B. Find the power produced by the locomotive's engine. We know that power is given by the forward force times the velocity it is traveling in. In the previous question, we found the forward force to be 0.2 newtons. So we can substitute our forward force and the velocity at which it is traveling at, which is 2 meters per second, to find the power. The power produced by the locomotive's engine is now changed to 1.2 watts. Part C. Find the magnitude of the tension in the coupling at the instant the locomotive begins to accelerate. So let's take a look at this diagram over here. This entire system is now altered. So we can find the forward force, which is now acting as a result of the increased power, using the power is equal to forward force times V formula. We can subject F to find the value of F. So power in our case should be equal to 1.2, which is the new power. And the value of V should be the same as before, which is 2 meters per second. Once we simplify, we find the forward force to be equal to 0.6 newtons. Okay. Now, when we consider the system, our values of tension get cancelled out. In that way, the calculations become simpler. We can use Newton's second law to find the resultant force acting on the system, and then we can subject A to find the acceleration acting on the system. So the forward force acting on the system is 0.6. The only backward force that's acting is the resistance to motion. That's 0.2 newtons. We can decrement that from 0.6 and set that equal to the total mass of the system, which is mass of the truck plus mass of the locomotive. And we can subject A, and we find the value of A to be 0.333 meter per second squared. We're not done yet. We need to find the value of t, so we can consider any one of these two individual elements of the system. So let's consider the truck. So the forward force acting on the truck in now is equal to t, and the backward force is equal to 0. We know the mass of the truck, which is 0.4, and the value of A, which is 0.33. That's 1 over 3. And we can find the tension to be equal to 0.133 newtons. Problem number 5. The diagram shows a block D of mass 100 kilograms supported by two sloping struts, AD and BD, each attached at the end of angle 45 degrees to fixed points A and B respectively, on horizontal floor. The block is also held in place by a vertical rope CD attached to a fixed point on C on horizontal ceiling. The tension in the rope CD is 500 newtons and the block rests in equilibrium. So the weight of the block is 100 G newtons, and it's acting downwards. Since the tension is less than the weight, there must be upward forces acting on the block that allows it to be in equilibrium. So the forces exerted by AD and BD should act upwards. We can extend the line of action of this force so that it's easier to draw diagrams and understand the situation. So this is FAD and FBD. Let's draw our horizontal axis, and the angle at which FAD works from the horizontal should be also equal to 45 degrees, as these angles are corresponding angles. And the same goes for FBD. Now we can divide FAD and FBD into its components. So the vertical component of FAD would be FAD sine of 45 degrees, and the vertical component of FBD would be FBD sine of 45. Horizontal components are just FAD cosine of 45. And the horizontal component of FBD is FBD BD cosine of 45 degrees. Okay. Now we'll just have to consider the vertical and horizontal forces. So since the system lies in equilibrium, the sum of the horizontal forces should be equal to 0. Therefore, the force on the right hand side, which is FAD cosine 45, should be equal to force on the left hand side, FBD cosine of 45. Equating them would give us this relation. Cosine 45s get cancelled, and we can safely assure you that the magnitude of FAD is equal to the magnitude of FBD. Okay, now we will consider the vertical section. So in the vertical section, FAD plus FBD, both of them multiplied by sine of 45, is equal to the weight, which is 100 G. Since FAD is equal to FBD, we can just say the sum of those two is equal to 2 FAD sine of 45. And also there is a tension that's acting on the block in the upwards direction that's of magnitude 500 newtons. We'll also add that in. And all of that is equal to the weight of the block, which is 100 G. We subject FAD, and we find FAD to be 354 newtons. And since FAD is equal to FBD, FBD is also 354 newtons. A horizontal force of magnitude F newtons is applied to the block in the direction parallel to AB. Find the value of F for which the magnitude of the force in the strut AD is 0. Okay, so for the force in the strut to be AD to be 0, there must be another force that acts as FAD. So since the horizontal component, since the entirety of FAD is acting towards the right hand side, for FAD to be replaced by F should act on the right hand side as well. So since F is in the direction of AB, okay, our new force, so let's say FAD is equal to 0, so all of this, let's just get rid of our F80. So our new force, which is F, should work on the right hand side because it has to replace, or it has to work for the missing force that was F80. So our new diagram should look like this. All right. So in this scenario, things are a bit more simpler because we don't have to divide the right-hand side forces into components. It's just one horizontal force. So if we consider the horizontal this time, F would be simply equal to FBD cosine of 45. Thus, F would be equal to FBD cosine of 45, all right. Now we'll consider the vertical. In the vertical, only FBD sine 45 exists, and along with the tension in the upward direction, and which is equal to the weight of the object. There is no FBD sine 45, F80 sine of 45 because that has been removed. So if we solve for FBD in the new scenario, we'd get 500 sine of 45. All right, we know the value of FBD. We can substitute that in our original, in the expression that we found using the horizontal forces. Once we substitute the value and simplify, we find F to be equal to 500 newtons. Problem number 6. A block B of mass 2 kilograms lies on a rough inclined plane sloping at 30 degrees to the horizontal. A light rope inclined at an angle of 20 degrees above a line of greatest slope is attached to B. The tension in the rope is T newtons, and there is a frictional force of F newtons acting on B. The coefficient of friction between B and the plane is mu. It is given that F is equal to 5, and that the acceleration of B up the plane is 1.2 meter per second. Find the value of T. Okay, in this first problem, we have to take into account the forces that are acting along the plane, which are, parallel to the plane. So first things first, let's divide our weight of the block into its components. So this is the weight, 2g. So the weight that acts along the plane is, so we're going to add the component of the weight with F. That's going to be 2g sine of 30. And the horizontal, or, well, the component of T that's along the plane would be T cosine of 20. All right. And since the block is accelerating along the slope in the upwards direction, with A being equal to 1.2 meter per second squared, we can use Newton's second law to make a relationship between all of these forces. So resultant force is equal to MA. The forward force, which is T cosine of 20, minus the backward forces, that is F, which is 5 as given, minus 2g sine of 30, which is the component of weight acting backwards, will be equal to the mass of the block times the acceleration. When we subject T, we find T to be equal to 18.5 newtons. Part 2. Find the value of mu. So, as the block is accelerating up the plane and it's moving, we can safely say that the frictional force acting on it would be equal to mu times r. This is only true when the block is, number one, either in limiting equilibrium, or when the block is accelerating or moving up the plane. So since the block is accelerating up the plane and moving, mu r would be equal to F. But before that, we have to divide the weight into another one of its component, which is perpendicular to the line of the greatest slope. So this would be equal to 2g cosine of 30, okay? And the reaction force that's acting on the block would be acting upwards. We're not done yet. We have to divide T into its vertical component as well. So the vertical component of T would be T sine of 20. Okay. Now we have to just consider the vertical forces only. And since the block isn't moving in the vertical in the perpendicular direction to the line of greatest slope, we can safely say that the top force that's acting upwards to the plane is equal to the downward force that's acting downwards to the plane. So t sine of 20, which is the upward force, would be equal to 2g cosine of 30. If we subject r is found to be 10.99 newtons. Now coming back to F equals mu r, we know the value of F, which is 5. We know the value of R, which is 10.99. Thus we can take the ratio of F to R to find the value of mu. Part B. It is given instead that mu is equal to 0.8 and t equals 15. Determine whether B will move up the plane. So first, let's just modify our diagram according to the new information. So no acceleration is acting on the block, it's not given. There is, yeah, that's basically it. There's just no acceleration acting on it. And instead of t being unknown, we will just have to replace that with 15. So 15, 15. All right. So let's think of this scenario. So in this given information, it's not stated whether the block is in limiting equilibrium or whether the block is accelerating up the plane or the block is about to move up the plane. So for the block to move up the plane, the block must enter limiting equilibrium first. That means the block is about to move upwards along the plane. And if the block moves upwards, the frictional force must act in the opposite direction of motion, that is, downwards. Alright, so if the block is in limiting equilibrium, F would be equal to mu r, and we'll just have to see if the backward forces is whether the forward force is greater than or equal to the backward force. Only then will the block be able to move upwards. So let's divide our t into its components. We've already done that. So let's take into account the horizontal component first. So that would be equal to 15 cosine of 20. Thus, the horizontal component of the forward force of t is 14.1. Now, let's take a look at the backward forces. If the block is in limiting equilibrium. So if the block is in limiting equilibrium, F would be equal to mu r. Before that, we have to find the value of our reaction force. So, as you can see from the diagram, r plus 15 sine of 20, which is the vertical component of t, is equal to the weight component. Thus, we can easily find the value of r from that, and that's approximately equal to 12.9. From that, we can find the value of F. We know the value of mu, which is 0.8, and the value of r. So F would simply be equal to the coefficient of friction times the reaction force. Thus, the frictional force acting on the block is 9.75. Alright, now since we know the frictional force, we can easily find the backward force that's acting on the block. And that would be the sum of the frictional force and the weight component, which equals 19.8. Alright, since the backward force is 19.8, for the block to be in limiting equilibrium, or to move upwards, the forward force must also equal 19.8. But as we previously found out that the forward force is only 14.1, thus we can conclude that since the forward force is less than the backward force required, B will not move up the plane. Because the minimum force that's required for limiting equilibrium, the minimum forward force, is 19.8. Problem number 7. The diagram shows a smooth track which lies in a vertical plane. The section AB is a quarter circle of radius 1.8 meter with center O. The section BC is a horizontal straight line of length 7 meter, and OB is perpendicular to BC. The section CFE is a straight line inclined at an angle of theta above the horizontal. A particle P of mass 0.5 kilograms is released from rest at A. So let's just quickly draw that. Particle P collides with particle Q of mass 0.1 kg, which is at rest at B. So this is Q, 0.1 kg. Immediately after the collision, the speed of P is 4 meters per second in the direction of BC. You should also assume that P is moving horizontally when it collides with Q. Show that the speed of Q immediately after the collision is 10 meters per second. Okay, so as P moves downwards, its gravitational potential energy is slowly converted to the kinetic energy. So at B, all of its kinetic energy, all of its gravitational potential energy is converted to kinetic energy. So using the law of conservation of energy, we can safely say that the GPE that was lost would be equal to the kinetic energy that is gained. So we can now solve for V, and V is found to be 6 meters per second. Now, using the conservation law of momentum, we can say that the momentum before is equal to the momentum after. So the momentum before of the system is just 0.5, which is the mass of P, times 6, which is the speed at P at which it collides with B. And the momentum after the collision is just simply the mass of P times the speed of P after the collision. It's given in the above text, plus the mass of Q times the velocity of Q, which is what we are here to find, the speed of Q after the collision. So we can then solve for Q, and Q is found to be 10 meters per second. When Q reaches C, it collides with a particle R of mass 0.4 kg, which is at rest at C. The two particles coalesce. The combined particle comes instantaneously to rest at F. You should assume that there is no instantaneous change in speed as the combined particle leaves C, nor when it passes through C again as it returns down the slope. Given that the distance CF is 0.4 meters, find the value of theta. Okay, so let us consider the small section of the diagram that is CFE in the next page. Alright, so we know that the particle R is at rest at C, that is 0.4 kg, and the particle Q of 0.1 kg is approaching R with the speed 10 meters per second. Alright, we also know that the section CF is of length 0.4 meters. Alright, so as Q approaches R, as it's approaching R, and when it's in contact with R and combining with R, coalescing with R to form the new particle, we can find the velocity of the combined particle using the law of conservation of momentum. So we know that the momentum of the system before the collision and combination is the mass of Q times the velocity of Q plus the momentum of R, which is 0 because R is at rest. That would be equal to the velocity of QR times the total mass of QR. So this is the momentum of the combined particle. We can then solve for QR, and QR is found to be 2 meters per second. Alright, so let us draw QR now. So QR is a larger particle of mass 0.5 kg, and it's traveling at 2 meters per second. Okay, let us consider this triangle CFE, or CF, and this unknown side. Let's call this X, CFX. It's a right angle triangle. We can find the maximum height that's gained by this particle, okay, QR, and then we can use trigonometry to find the value of theta. So for QR to reach a maximum height, all of its kinetic energy should be converted to GPE. So we can use the law of conservation of energy. KE lost by QR is equal to height gained by QR. The KE lost would be equal to half times the mass of QR times the velocity of QR, which would be equal to the mass of QR times G times H. The masses get cancelled out, and if we solve for H is found to be 0.2 meters. Okay, So let's add our h in the diagram, which is 0.2 meters. We know the opposite side of the triangle, the opposite side. We also know the hypotenuse. Therefore, we can input that in our sine function. Sine equals opposite over hypotenuse. Opposite is 0.2, hypotenuse is 0.4, and then we can find the value of theta, which is 30 degrees. Part C. Find the distance from B at which P collides with the combined particle. Since we're dealing with many particles here, it's wise to divide the problem into many parts. So let's take a look at the first part when we're only dealing with P and Q. So as P collides with Q, after the collision, the velocity of P is basically 4 meters per second. It's given in the previous text over here. It says that immediately after the collision, the speed of P is 4 meters per second. All right. So as Q moves towards R with 10 meters per second, P is also moving towards R, okay, with 4 meters per second. So when Q collides with R, there's some time spent. And we can simply find that time by using the distance traveled by Q divided by the velocity of Q. And that is found to be 0.7 seconds. All right? So within this time frame, we can find the distance that P travels. And that would be given by the speed of P times the time taken for Q to reach C. And that is 2.8 meters. So we've already found one part of the distance that they asked for. Now let's take a look at the second part. So we're now dealing with QR, okay? QR moves upwards with velocity 2 meters per second, and then it moves downwards again with velocity minus 2 meters per second because it's in the opposite direction. So we need to find the time that's spent for QR to go to F and then return to C. The time taken for this entire journey, basically. So we know the initial velocity of QR, which is 2 meters per second. We know the final velocity at F, which is 0 meters per second. We know the distance traveled, which is 0.4 meters. We can use the kinematics formula. S equals half times U plus V times T. S is 0.4, U is 2, and final velocity is 0. We can find T to be 0.4. As the magnitude of the acceleration when QR is moving upwards is the same as the magnitude of acceleration when QR is moving downwards, and since the distance is also the same, we can say that the time taken for QR to go to CF is the same as the time taken for QR to return to C from F. So we can just double the time that we found to find the total journey of QR. So as QR is doing its journey, P is still moving. How much distance does it move? Basically, the speed of P times the time taken for QR to complete its journey. So the distance of P would be equal to 3.2 meters. So we found the second part to the distance that we were told to find, that is SP2, and that is 3.2 meters. Now we'll take a look at the third part of our entire journey, when P is approaching QR and QR is approaching P. Alright, so we can find out the time taken for which P collides with QR by using a set of equations that model the displacement of P and the displacement of QR from B. So let's take a look at the P equation. So the displacement of P would be given by the distance or the displacement that is already traveled plus the speed of P times the time, the rate at which basically the displacement increases. So the sum of the displacements would be equal to SP1 plus SP2. That's the displacement that it has already traveled. And the rate at which the displacement increases is equal to 4 meters per second. That would be multiplied by the time. Therefore, the displacement of P from B would be given by 6 plus 4t. Now, for Q, displacement, instead of it being an increasing displacement equation, it is a decreasing displacement equation because it is traveling in the opposite direction and towards B. So, when time equals 0, the displacement of QR from B would be equal to 7, and the 7 would be decreasing at a rate of 2 meters per second. Therefore, our decrement factor would be minus 2t. When these two particles collide, they will be at the same displacement from B. Thus, we can conclude that SP is equal to SQR. When solving for t, we get t to be equal to 1 over 6. So at t equals 1 over 6, after QR is at C, the displacement of P, or the distance traveled by P in that short time period, would be simply given by the speed of P times the time taken for these two particles to collide. And that is found to be 2/3. All right, now we have all of the three sections of our displacement. We can simply add them together to find the final answer, which is 6 and 2/3.